Have you ever wondered how database indexes are stored and how they're used to locate tuples? Do you know what a B tree is? And what's the difference between a B tree and a B plus tree? And what are the advantages and the limitations of each? Well, we're going to answer these questions in this video, so let's go. Hello and welcome. I'm Elhelw. In previous videos, we talked about storage for databases, how the tables are stored, all the stuff about files, pages, and tuples, and so on. We talked about different ways to organize the data pages. If you haven't seen these videos yet, I'm gonna put the link up here on the screen and also down in the description, so feel free to check it out. Today, we are going to talk about indexes. What's an index? How is it used to make queries faster? And how is it stored physically in the database? What kind of data structures are used and so on? Some people have asked before about data structures and algorithms and what's the use of knowing that for someone working on databases. Well, I think today you're going to find out. So let's check first, before we get into indexes. How do we look for a value inside a table? For example, imagine that we have this huge table that has millions and millions of rows. And we want to look for the row or rows that have a specific value. Let's say there's the attribute x, and we want to look for the rows that have x equals to 25. How do we do that? Basically, what we can do is that we're going to have to go over the whole table, check each row, find the attribute x in that row, check if it has the value that we're looking for, and if that's the case, we're just going to return it. How expensive is this? Remember, the data in tables is stored in pages, right? So if we look at the table like this might be kind of like the conceptual way of looking at the table. And if we're dealing with a huge table, then it has lots and lots of pages. And we want to look for this particular value, right? So we're going to load the first page into memory, go over the tuples in that page one by one. For each of these tuples, we're going to locate the attribute x that we're looking for and see if it's equal to 25 or not. If it is, then we return it. We go to the next tuple and the next and the next and so on until we finish the whole page. Once we're done with that page, we're going to load the next page, do the same thing, and then the next and the next, and keep doing that for all the pages in the table. This is called a full table scan. Pretty obvious name because we're scanning the full table. Every single page in that table is being scanned. Again, for large tables, this is a lot of work. It's super slow. We try to avoid this as much as possible whenever we can. So how can we make this faster? One idea is, can we do this in parallel? Instead of just scanning one page at a time, can we do this in parallel somehow? Yes, we can. We can do it in a multi-threaded fashion, for example, have multiple threads working at the same time. Instead of just one thread scanning every page in a sequence, let's say we have a couple of threads running at the same time, each of them scanning a subset of the pages. That's great. I mean, that definitely would make it faster. However, it still includes scanning all the pages, even though they're not done in sequence. It's also more complex to implement because now you have to take care of this, the multi-threading business and how these threads work. You also have to think about your CPU, how many cores you have, because if the number of cores is less than the number of threads, then you might have some bottlenecking happening. So now you have to worry about the CPU as well. So it is not the best thing out there. It helps, but it's not the best thing. So what else can we do? Another thing we can think about is partitioning. This is a very solid technique. It's used in many databases. The idea is, instead of looking at this table as one big thing, we can split it into multiple smaller tables based on, in this case, the value of the attribute x that we're looking for. So basically we say, okay, all the tuples that have x between 0 and 10 are going to be in one partition, x between 10 and 20 are going to be in the second partition, and so on. So now it's basically like we're dealing with a bunch of smaller tables, right? And when we want to look for x equals 25, then we can go directly to the partition that we know has this value. So in this case, we're going to go to this partition. We're not even going to look at the other partitions because we know for a fact that this value cannot be there. So we already excluded a bunch of pages that we're not going to look at. And then we're going to scan the pages in this partition like we did before. Does this make it better? Yeah. I mean, we already excluded a whole bunch of pages that we didn't even look at, so that's much less I/O than we did before. So it's faster than scanning the whole thing, and it is also simple to implement. Once you define your ranges, you know which partition to go to and which partition to scan. The disadvantages of that, or like the things that this does not handle, first of all, partitions are not all the same size, right? Like it depends on the distribution of the values in X in this case. One partition might be huge if most of the rows kind of like fall in this range. Others may not have that much data if only a few rows fall in this range. So you have to think about your partitioning, what are the boundaries of every partition while you're creating the table, depending on your knowledge of the data. But yeah, again, like one partition might grow too big and then it becomes almost like scanning the whole table, right? So you never know. Also, writing becomes slower because now as you write new data, you have to figure out which partition this data should go to. So that kind of like adds a little bit to the writing cost. Thirdly, if we are partitioned on column X or attribute X in this case, what do we do if we're looking for a value that, let's say, attribute Y is 20, right? We don't know which partition that would be in because the partitions are based on attribute X. So whenever we're looking for a different attribute, we still have to scan the whole table. So that doesn't help us a lot with this particular case. Again, it's still a useful technique and it's used in multiple systems, but usually it's not used by itself. We have to use it in conjunction with other things. The third thing is what we're going to talk about today is indexes. So indexes are also used to try to minimize the number of pages that we are reading. What is an index? How does it work? Think of it conceptually like the index that you find at the end of a book, right? So if you go to the last few pages of the book, you'll find this index that has all the words sorted alphabetically. You can find any word that you're looking for by kind of like, skimming through the index. And once you find it, you'll see in front of that which pages this word is on. Same idea here. So you'll have some structure that has all the values and then a pointer to where that value is stored. The values are also sorted, just like the book analogy, where these values are sorted alphabetically. Here will be sorted by whatever, if it's numerical, if it's date, whatever, it'll be sorted by that type. So conceptually, you can look at it like this. So we have the table, all the pages in there, and then we have this auxiliary structure, which is the index that has in this particular case, all the values of attribute X, and each of them also points at where this row is located on disk. All the techniques that we've talked about, whether it's parallel processing or partitioning or indexing, basically the high level goal that we're trying to achieve is reducing the search space, right? Reducing the number of pages that we are accessing. The more pages that we can exclude means less I/O, means faster processing. So we're trying to exclude as many pages as possible. The more pages you can exclude, the better. And remember this because we're going to say this kind of multiple times throughout this video. This is the main goal that we're trying to achieve. We're clearly trying to avoid scanning the whole table because that's extremely slow. But how little can we get in terms of I/O? This is what we're going to see. So indexes are clearly a great way to do that. But the question becomes, what kind of queries can indexes help with? So the one example that we've seen is looking for a particular value. This is called a point query. So we're looking for a given single value. The result might be a single tuple or multiple tuples, depending on whether this value is unique or not. But either way, we're looking for a single value. This is a point query. The other kind of queries that is very common also is a range query. When we're looking for values between, within a certain range, this could be something like X is greater than 10. So like anything above that value, or X is less than 100, or X between 20 and 30. So those are ranges, not a single value. So this is the second type of queries that indexes can help with. Now, how do we store an index? We kind of know how it works kind of conceptually, but how is it stored to make that as efficient as possible? Let's look first as kind of naive approach, if someone doesn't know much about data structures, how would we store indexes? So we could say, okay, let's store it the way we just explained it, kind of in the conceptual way, right? So we've seen this figure already. Why don't we just store it like that, some sort of list that has all the keys or all the kind of the values that we're looking for and the pointers to the location. The values are sorted, and then each value kind of has this pointer attached to it. I mean, sure, let's take a look at that and see how that works. So how would we search for a value here? Let's say we're searching for x equals 25. So basically we're going to scan this list just like we do with the index at the end of the book until we reach the value 25 and then follow the pointer to go to the data. Is that good? I mean, yeah, it's we're not scanning all the table. We're going directly to the page that contains the data, so that's good. However, the problem here is that we had to scan the index, right? Like we had to scan all the values in the index until we reached the 25. Remember, the index is also stored in pages. And if you have a huge table that you're building an index on, this means that the index is also usually, big. I mean, not as big as the table, but it's still big. So it has multiple pages. And we had to scan, all these pages until we reach the value that we're looking for. So that's not great. Basically, we call this, O of n, because it's linear in the size of the index. If the value that we're looking for happens to be near the end of the index, we still had to scan all of it until we reach that value. So not great. Someone might ask, well, hey, wait a minute, the index is sorted, right? If it's sorted, why do we have to scan? Why don't we do like a binary search or something? We can do binary search for sorted lists. True. However, if you try to do that here, again, remember we're dealing with pages. Pages are on disk. If you try to do binary search, meaning like you're gonna go to the middle page somehow, and then based on that, you might go earlier or later, and then you might read the same page again if you kind of like get closer to the kind of like to the middle. This is random access. Now you're like jumping back and forth between different pages. We try to minimize random access on disk as much as we can. So this is not great. This is gonna be expensive. And also, yeah, multiple reads for the same page. I mean, cache might help with that, but not always. But again, this is going to be expensive to try to do binary search here, so linear approach is what it is. This is also not great for updates or insertions, right? If we want to insert a new tuple, for example, so first we have to locate where it needs to go in the index. Like we have to update the index. So let's say we insert a tuple that has x equals 40. So we have to search the index, figure out where it should go, add that new entry, and then we have to shift everything after that to maintain that it's still sorted. So it's a costly operation. So again, not great. Obviously, no one stores indexes like that. It was just kind of like, to illustrate this point. So we need a better data structure, not that list. Well, I mean, wait a minute. I just said binary search, right? Like, don't we have something called a binary search tree? Can we use that? I mean, let's see. If you don't know what a binary search tree is, let's first give an overview on what that looks like. So a binary search tree, or we refer to it as a BST in short, it's a binary tree. So each node can have up to 2 children. It is also sorted in the sense that for each node in the tree, all the nodes coming from its left subtree are less than the value of that node, and all the nodes on the right subtree are greater than or equal to that node. Let's see that in the example. So we have this tree here. If we look at the root node that has value 8, we'll see that everything on the left subtree is less than 8. Everything on the right subtree has to be greater than or equal to 8. And the same thing applies if you look at any other node and its left and its right. How does that help us? How can we use this as an index, right? So the idea basically is that we can use this tree to store like the keys that we're looking for. Again, like if we're looking for x equals something, so the values of x will be stored in this tree, and each node will attach to that the pointer that points at where the data is stored. So instead of putting them in a list, we're putting them in this binary search tree. And it has to be also sorted, with the same rules of the BST. So like, the left and right has to be less than and greater than and so on. Let's ignore the data pointers for now and just focus on the values here in the tree, right? But remember that these pointers are attached somehow, and we'll come back to that later. So given that we have this structure, how do we search? Let's say we're searching for x equals to 6, right? We're going to start from the root. Usually dealing with any tree starts from the root. So we're going to look at the root. We have 8. Okay, but we're looking for 6. 6 is less than 8. So this means that we need to go to the left side. So this check, visiting the root node and figuring out which direction to go, basically means that we don't need to consider anything on the right side. So we kind of like already excluded almost half the index. We reduce the search space, as we were saying earlier, right? Okay, now we check the next one. We're looking at the node that has value 3. Again, we're looking for 6. 6 is greater than 3, so we need to go to the right side. So again, excluding everything on the left, go to the right side. The next node that we are at, this is the value of 6. This is the value that we're looking for. So now we can just follow the data location to the page that has the data. So this is how it would work using a binary search tree. As I said, each check or each node we're visiting kind of like almost reduces the search space by half of what is remaining. So we're excluding half the index, and then next time we're excluding half of what's remaining, and so on and so forth. This only applies, like the half thing only applies if the tree is truly balanced. In that case, we would get basically the complexity or the cost of looking for something in the tree becomes O of log n. There are several places where you can search for to find out the proof of that, but we're not going to get into this. So again, this is only happening if the tree is balanced. Binary search trees by default are not necessarily balanced. It can be unbalanced. What does balanced and unbalanced means? Balance means that for any given node, if you look at the right and left subtrees, the depth of those subtrees will be either the same or difference by 1. Like one tree might be 1 level extra. But ideally, they will be the same depth. The more balanced the tree is, the number of levels is less. So the number of checks that we have to do, the number of nodes that we have to visit would be less. What would make a binary tree unbalanced, right? It could be unbalanced because of the order of inserting data. If we happen to insert data, let's say in ascending order or descending order, you might end up with a heavily unbalanced tree. Something like we can see here. Like here, we're inserting more increasingly large data, so we end up always putting stuff on the right side, so the tree ends up becoming like this. This is pretty much almost as bad as the linear kind of like sequential list that we looked at first. If we're looking for 14, for example, we pretty much have to scan most of the index in this case. So this becomes ON pretty fast if the tree is unbalanced. So not great. Can we improve even further? Is there a structure that is better than a binary search tree? This takes us to the next one, which is the B tree. The B tree is also sorted in the same way as the binary search tree, in the sense that everything on the left must be less than the value and everything on the right must be greater than the value. Some differences here is that the nodes don't have just a single value and 2 children. It can have up to k children, so k is called the degree of that tree. So a node that has k children would have k minus 1 values or keys stored into it. So in this particular example, k equals 3, meaning that every node can have up to 3 children and 2 keys. It could have fewer, and generally a node has to be at least half full. So at least would be one key and 2 children in this case. If k is bigger, like k is 1,000, for example, you could have a minimum of 500 keys coming out of any particular node. The B tree is also balanced. It is guaranteed to be balanced all the time. It is self-balancing in the sense that the insertion algorithm itself may restructure the tree to make sure that it is balanced. So it will do some extra work to split some nodes, to move things between nodes to make sure that it is balanced the whole time. This clearly has a cost, right? Like the more work we do through insertion, meaning that the cost of writing is higher. So it helps reading, but it makes writing a little bit more expensive. There's always this trade-off, right? Like you cannot make everything better. One thing has to come at the expense of something else. So let's see an example of how this looks like, right? What happens during insertion. I'm not going to do this in the slides because doing this animation is a pain. But there is this amazing tool that's been developed by someone in the University of San Francisco. So we're going to use that to see how the insertion happens. I'm going to also include a link to the tool in the description, so you can feel free to play with it if you want. So yeah, let's see. All right, right now we have maximum degree equals 3. This means that each node can have up to 3 children, which means that it can have up to 2 keys in the node. So yeah, let's see what happens. So let's insert, for example, the key of value 2. So now, since this is the first node in the tree, we just created a new root. Now, if we insert 6, 6 is greater than 2. We have space in the root node, so we're just going to insert it in the root node as well. Now the root node is full. If we try to insert another node, let's say 4, for example, that should go between 2 and 6. However, because the node is full, now we have to split. So the middle value, which is 4, becomes the new root, and then 2 and 6 become its children. Now let's insert 5. 5 is greater than 4, so it should go in the right child, which already had empty space. So now we can add that to the right child as well. So now the right child has both 5 and 6. Now let's try to add another value that is greater than 4. Let's put 7, for example. So in this case, it should also go to the right child, but the right child was already full, so we had to split it. So the middle node in that, which was 6, had to be inserted up one level in the root. The root in this case had space, so we were able to do that, and then the rest of the nodes, the 5 and 7, split off, and each of them became its own node. So this kind of like illustrates how we do insertion in B trees, and you know how the splitting happens and all that. As I said, like aside from the balancing being like a huge improvement over binary tree, the other improvement being that each node can have multiple keys. The more keys that you can put in the node means that you need fewer nodes, right? Which means that the number of levels in the tree becomes less. So the number of nodes that we have to visit is much less. Again, we are reducing the space, reducing the number of pages. Usually each node is a page. So the more keys that we can put in a page, the fewer pages there are, the fewer pages that we have to load from disk, which means less I/O, less cost. Remember that, again, each key has a data pointer attached to it, right? So we should fill the page, you know, as much as possible. Like, you know, if let's say we know the size of the values, the size of the pointer, we can just add that and say, like, you know, a page can fit maybe, I don't know, 1,000 of those. Then, you know, we can have very few pages because we can put the values and the pointers as much as we can into these pages. How do we use this as an index, right? Like, how do we do the lookups here? Let's see. So again, this is an example of a B tree. We have some values. Each value points at the data somewhere. We're looking for x equals 27. So again, it's very similar to what we did with the binary tree, except that each node now has multiple values and multiple children coming out of it. So we're looking for 27. We start from the root node, figure out, like, is it less than 10, or is it between 10 and 20, or is it greater than 20? In our case, here it's greater than 20. So we're going to look at the third child. So this will take us to that next node. In this particular case, 27 is actually found in the node. So we're done, and we just, you know, follow the data. Let's see another example. Now we're looking for 12. Again, starting from the root, we look, where is this between 10 and 20? So we're going to look at the middle pointer, which will follow that to the next node. 12 is less than 14, so that's like the first pointer in the next node. Goes to that one. So 12 is found here. So the maximum number of checks that we did in this case is 3. The maximum number of nodes that we visited is 3. So the search cost here is log n. Again, let me reiterate. The main advantage of having to load only a few nodes is that this is, you know, fewer I/O. So this is better than the BST in this case. One disadvantage, or we already talked about, is the cost of writing and rebalancing the tree. So that's one downside. Another downside is, remember that each key is attached to it the pointer that goes to the data. This means that you have to take that into account while deciding how many keys can fit into a page. If we can somehow kind of like eliminate those pointers, or some of them in some cases, this would mean that we can fit more keys into one page, which would mean fewer pages to scan. So let's keep that in mind. Let's try to see how we can do that. So that's another issue that we maybe want to deal with. Another issue with the B tree is we've only looked at a point query. How do we do range queries here? Like if I want to look for x between 15 and 24, we've seen how to look at, let's say, if we want to look for 15, we just follow the same algorithm that we just did, and we will reach the value 15. But how do we get that whole range? From 15, we can go up again to get the next value, 17, and then go down to get the 18, and then go all the way up to get the 20, and then back all the way down to get 22, and then up again to get 23. This is ridiculous, right? Like it's very difficult to do that. First of all, we will need to read like some of those nodes multiple times, going up and down. We're going to pass by those same nodes, so that's already extra I/O. Secondly, in most cases, we don't even store the pointers that go to the parent, right? Like we only point from the parent to the child. So this means in order to do this, we have to store these extra information. So that's another kind of like level of complexity that's added. So this is clearly not the best way to do it. So we need a different data structure that will allow us to do these range queries in a more efficient way. Enter the B plus tree. What is the B plus tree, you say? It's basically like a modified version of the B tree that has some extra features. So the overall kind of like look is very similar. It still has these nodes, still has some degree. So like, each node can have, k children, k minus 1 keys. The difference is two main differences. One, the data pointers are only stored at the leaf nodes, not in every single node. This means that all the keys must exist at the leaf node so that we can, go from that to the actual data, right? So this means that the other non-leaf nodes are actually duplicates of what's in the leaf level. So if you look at this example, like, the value 15 is duplicated, the value 35, 45 are duplicated, 25 is duplicated. So everything that is not in the leaf node are duplicates from what we have in the leaf. But the data pointers, the data location, is not included in those intermediate nodes. It's only in the leaf. The second difference is that all the leaf nodes are pointing to one another. So you see those horizontal arrows in the bottom level. All the data nodes, or all the leaf nodes, are pointing to each other. The way insertion happens and rebalancing is also very similar to B trees. However, when we split a node, in this case, we take that first value and duplicate it. This is why we see duplicates in the tree. And we can see that in the example. I'm going to show it using that same tool. It also has a section for B plus trees. So let's look at that. So again, we have a B plus tree with maximum degree of 3, which means each node can have up to 3 children. So let's start. Let's insert the value of 2. Now we have a new node, which is the only node in the tree. So this is also the leaf node. Now let's insert 6, for example. 6 is greater than 2, but it can fit within the same node. So we're just going to add it there. Now let's add a new value, let's say 4. So 4 should go between 2 and 6. But this node is already full, so let's see how this works. So we try to add it there, but then we have to split. And since this is a B plus tree and all the keys have to be in the leaf level, so 2, 4, and 6 are all there, but the split, we also take this 4 and create a new level. And now, like, the right child has the value 2, the left child has 4 and 6, and they're pointing at each other here. Let's try to insert 5. So 5 is greater than 4, so it should go into this node, but this node is full, so let's see what happens. So it goes here, and then we have to split again, and then pull up the 5 upwards. So it's again duplicated, and then we have to split this into 2 nodes. So now we have 3 nodes in the leaf level. Again, each one is pointing to the next one, and now the root has 2 keys. So the root is also full. So what happens if we try to insert another one that is also larger? So 7, which should also go here. So now this one has to split. We insert above, but the root also has to split because it was already full. So we added a new level above as well. Now we have 4 leaf nodes that are pointing to each other, and a couple of intermediate nodes as well. So this is how insertion happens in B plus trees. All right, we've seen now how insertion happens in a B plus tree and how the rebalancing and all that takes place. Now let's see how to use this as an index to look for a particular value. So we want to look for x equals 20, very similar to how we did that with a B tree. So we start from the root and then go left or right or whatever child bin, depending on the value that we have and the values that are in this node. So start from the root, we're looking for 20, so we know we're gonna go to the right side because that's less than 25. We go to this node, which is 15, it has a single key so far. So again, we're looking for 20 that's greater than 15. So we go to this node, and then we find the 20 that we're looking for. This is for a point query. Does this work also with range queries? So what do we do when we're looking for x between 20 and 35, right? So again, to find the 20, we're going to do the same thing we just did. So go all the way from the top, all the way to the leaf node, we found the 20. But now, once we found that, we don't need to go up and down like we did in the B tree, right? We can just follow the horizontal links in the leaf level to get the next value, next value, next value, and so on. So if you look at the leaf level, it's already sorted. So we can just start from the 20, follow that link, 25, 30, and then 35, and now we've reached the last value that we want. So range queries are extremely efficient, extremely fast here. We don't need to do multiple pages. We don't need to go up the tree again. We just follow that leaf level. So B plus trees are good for both point and range queries. Also, since the intermediate nodes don't include that data pointer, this means we can fit many more keys into those intermediate nodes. So this means that we have fewer number of nodes all over to read. So that's another advantage over the B trees. The disadvantage is that we need to duplicate those keys, right? Like, some of the keys in the leaf level are duplicated also in the intermediate nodes. So that's kind of like a disadvantage. It uses a little bit more space, but this is way kind of like, outweighed by the benefits that we've just mentioned. So what is actually used in real database management systems, right? Most systems use B plus trees or some variant of them. There is some confusion in the database community. Sometimes people refer to things as B trees or B plus trees. Many systems that use something that looks more like B plus trees say that they're using B trees. The reason for this is because B trees can actually refer to two different things. It can refer to the B tree, the structure that we actually talked about earlier, or it can refer to this whole category of data structures, including B trees and B plus trees and a couple of others. So all of these fall under one category called B trees. Confusing, I know, but that's how it is. So when they say B trees, they're usually referring to the whole kind of like category. Also because maybe their implementation is not quite B plus tree, but it's also not quite like the original B tree either. It's somewhere in between. An example for that, if we look at Postgres, for example, right? It uses a structure that looks like a B tree, but it also does not include the data locations except in the leaf level, which is a B plus tree feature. But the leaf level does not have the links that point to each other. So it's kind of like somewhere in between a B tree and a B plus tree. The same thing also applies for MongoDB. Some of these systems do it this way because of like some implementation detail that trying to optimize certain features. So they do it in a little different way. But I mean, it's kind of like, the same concept. So if you read the documentation for any of these systems, just keep that in mind that it might be somewhere, in between B tree and B plus tree in the sense that we have talked about today. In most systems, as we've been mentioning, like, the leaf level of a B plus tree, it has this location pointer that points at the data pages to go and fetch the data once you've reached the node that you want. You'll see that in Oracle, in DB2, in Postgres, in SQL Server, and all those systems. Some systems also provide an alternative way of storing things. There is this index organized tables or IOTs where the data is actually stored in the index itself. So instead of having a pointer that goes to the data page, you actually store the data in that index page itself. So you navigate the tree. Again, the intermediate nodes only have the keys, but once you reach that leaf level, instead of having to follow a pointer, you're going to find the data right there. This means that the leaf nodes are much, much bigger, so you need way more leaf nodes. But at the same time, you find the data much, much faster. So that's another way of organizing the data. This is, I think, supported at Oracle and SQL Server, MySQL, SQLite. So some systems support this. So as you can see, like some of the systems support both ways of doing things, depending on, I guess, like you can probably choose, or maybe the system can set this automatically in some cases. So yeah, this is how indexes are used in terms of looking for data and how they are stored in most systems. All right, to summarize what we've talked about how to look for particular values. We've seen the full table scan and how expensive that can be. We've tried to see if we can find a way to minimize the number of pages that we're reading. We've talked about parallel scanning, we've talked about partitioning, and we've talked about indexes. We've seen how indexes can help for range queries and point queries. We've also looked at how indexes are stored in the database. We've considered a bunch of data structures, and we realized that the B plus tree is the most efficient one, and this is what most database systems actually use to store their indexes. As I mentioned before, indexes, they make reading much faster, but there is an added cost to writing because every time you write, you have to update the index, and in B plus tree, you have to also do the splitting and the rebalancing and all that. So you have to take that into account when you are deciding whether you need to build an index or not. What does your application look like? Is it read intensive or write intensive? And based on that, you can decide what you can do. Indexes are a big topic, and it's very important in query processing and query optimization. There's a lot more to talk about. There's, cluster indexes, covering indexes, multi-key indexes. There's a lot more to cover, but I will cover that in a separate video. If you want to get all the updates about the videos, please subscribe to the channel. If you found this video useful, please like it and share it with others so that more people will get to see it. And with that, we reached the end of our video. See you next time.